Okay, welcome back. So last time what we did is we configured Altium and we set grids. This time we're going to go back and start actually developing the schematic. So this part is going to be how to use the schematic, how to place components, how to find components in a library, how to find components in a vault, and how to wire components, how to use ports, how to use net labels. And I want to first of all, we closed Altium from the last video we did, and I want to show something that happens a lot to students when they're using Altium, and it's a mistake that you want to make sure you don't make. So we had our project open in Altium, it was saved, and then we closed Altium. And I'm going to show you what happens when we go back and open up Altium. So when we go back to open up Altium, you'll see that we had our same files are here. So we have our board and our schematic that we had created last time. So we could right now basically start adding components to this. The problem is what happened is when we reopened the software, it opened up all the documents that were still open when it was closed last time, but it didn't reopen those as a project. So you'll see they're listed right now as free documents. So any changes we make to these are not actually changes we made to the original project we created. They're just changes made to those files that were in the project. So we always want to make sure when we open up Altium, if we hadn't closed everything up before we left, to close everything up and then actually open our project. So we're going to go open project here, file open project. And there's the project that we had created before. And now we have that same schematic and board, but now these are actually open within our open demo project. They're not considered free documents. This is a big mistake students make. I've seen a lot of students make a lot of changes to a document not as part of their project, and it can really mess up their design. So it's important that we sort of pay attention to this. There's another thing I want to talk about that I didn't talk about last time, and that was how we navigated around in Altium. So just talk about some of the controls. You can't see my mouse, so I want to talk clearly about these things. So one thing we can do is, if I use the scroll wheel on the mouse, which I'm doing now, we're going to sort of pan up and down. We're going to make the screen sort of zoom up and down. If I zoom in, the way I zoom in or zoom out is I hold down the control key, and then I use the scroll wheel on the mouse, and I zoom in and out. Now the way I move around is the way I can move this sheet around, and this works in the board too. The board and the schematic have the same navigation. If I right-click, it sort of grabs the sheet and moves it around, which is a good way to sort of move around our design. So again, right-click and move around. Scroll wheel scrolls up and down. Control scroll wheel zooms in and zooms out, and that's really the main controls you need to know. There are other controls that you can do. For instance, this is control right-click, but for the most part, right-click to move around, control mouse wheel to zoom in and out are going to be your main controls that you use. Okay, so let's go back. So again, we're making sure our grid is 10. What we're going to do is we're going to start our design now, and the design I've chosen for this demo is a fairly simple one. It's going to be a board that takes an input 5 volts, so its input is 5 volts and ground. Could come from a USB supply, could come from a power supply. And what we're going to do is we're going to build a circuit that converts a 5 volt signal to a plus or minus 5 volt signal. So this would be used for something like powering the rails for an op amp. It's useful sometimes to have a negative voltage relative to your ground reference for things like differential op amps. So this is going to require us to add a DC-DC converting regulator. It's a special type of converting regulator. It's also going to require us to add components for that switching regulator. So to begin, and we're going to get that, I'm sorry about that message. I thought I disabled it, but I guess I didn't. So to start, we have to have a way of making a connection to our board. There's lots of ways to do that. So we could have a ribbon cable connecting to the board. We could have a USB port. We're going to do something simple this time. We're just going to do a header. So we're going to do a standard 0.1 inch spaced header connection for this board. And that could be you connect pins to that header connection. Could be you directly solder to it. A 0.1 inch spaced header is a fairly good sort of universal way to make a signal connection to a board. It leaves you with a lot of options. So there's a couple different places we can get parts. So in this case, we're looking for a schematic component or a part, a component that is a header, that represents a header. This should be something that symbolically shows the header connection in the schematic and then shows the actual physical construction of the header in the board, in the corresponding board component. So there's two main places we get parts. There's three places actually. One is we can get them from a library. So libraries are they're usually sort of local collections. This is a file that holds a bunch of design files for different components. There's also vaults. Vaults are sort of an online repository for components. The neat thing about vaults is they're basically kind of they're a way to rigidly structure managing resources. So in the case of a vault, you can have one centralized location where you store all these components. If you're working for a company and you have dozens of people accessing the same components, it lets people sort of make changes to components, update different versions of a component, and it allows everybody using that component to have some control over, do I use the updated version? Do I roll back to a previous version of the component? And so it kind of just, it's a better form of managing parts when you have lots of people working on the same thing. So we're going to start, the header is something that we can get, just from a library. So there's, if you look at the libraries, there's three libraries here. There's miscellaneous devices and connectors. These are libraries that come with Altium, and they're fairly limited. We don't use them for very many things, but for things like a header, they'll work just fine. Then there's this EE Schematic library. So the EE Schematic library, this is a collection of components that we use, that we've used within the EE department here. These are common things that students end up using. A lot of these things are things we already have in stock. So it's good to look through the components that we have here, and if you use them for your design, there's a good chance you can find them fairly easily. So you'll notice when we click on these components, it shows both the schematic symbol as well as the board design. And in this case, there's a lot of 3D bodies for a lot of these components. And so it shows those details here. What happens if we're looking at these libraries here, and let's say we accidentally click the X. So if we want to make the library sort of retool, we can just move out of the library there. But let's say we were looking at the libraries and we accidentally went bop, and we made it go away. Now this is where, and I know my face is probably covering up most of these, so I might sort of window this guy. Whenever we lose the library or the vault tab, we can always get them back here. So if we go down to these little menu items down here, we can go to System, Libraries, and that'll bring us back that library thing, so it's not lost forever. I know a lot of students get frantic sometimes, and they, when they lose something, they kind of freak out. Well, you can always find it. Just go back down here and click that. This also gives you, there's a lot of control down in that window down there. So let's go back to the miscellaneous connectors. This is where we're going to find the input to this board is going to be a 2-pin header. So to find that, we're going to go down to this header 2. We're going to right click that and we're going to go place header 2. And what that does is that gives us the header. We have mouse control with it. If I want to rotate this header, which I do in this case, I can press the space bar. Space bar rotates the header, and I can place it where I want. And you'll notice if we zoom in, the header is actually snapping to this course grid. So the header is snapping to this grid. So wherever we place it, it's going to be aligned. Okay, then we can hit escape to end that, to cancel that. So the input to our chip to our board is going to be plus 5 volts and ground. The output is going to be plus 5 volts ground and negative 5 volts. So what we can do is we can go ahead and also add a 3-pin header. So let's go to the 3-pin header here. Again, place that header. And maybe we'll put it right here and hit escape. Okay, so now we have our 2 headers. Those give us our connections on and off the board itself. Now within the board, we're going to have to do this conversion. We're going to have to convert this 5-volt signal to a negative 5-volt signal. To do that, we're going to use a DC to DC regulator. This is a switching regulator. This is actually a charge pump regulator. So this is different than some of the DC to DC switching regulators you may have used or we've talked about. These do not use magnetic storage. So the way a charge pump works is essentially you're charging up a capacitor. In this case, you're connecting the capacitor to the 0 and 5 volt signal. And then you are taking that charged capacitor, and you are, through a series of switches, reconnecting that capacitor where the lower potential side of the capacitor is connected to your negative signal, your negative pin, and the high potential side of your capacitor is connected to ground. So you can think of it as you charge. This is fairly easy to think about. You could do this just manually. You take a capacitor, you hook it up across the terminals of a 5-volt supply, and then you disconnect the capacitor and move the high potential side of the capacitor to the ground reference. Well, now the low potential side of the capacitor will be a negative 5-volt signal. That's what a charge pump, in this case an inverting charge pump regulator, does. It just uses a collection of FETs to do this sort of switching with the capacitor. The cool thing about this is it allows you to do a relatively small design, but with the exception of the inverting case, these charge pumps are fairly efficient. Using charge pumps to do voltage regulation other than just a clean one-to-one inversion, you start to get really inefficient. So I think charge pumps are sort of about maximum 50% efficiency for doing larger voltage changes. So let's look. This is the part that I sort of pre-shopped around for a switching regulator to do this. This is on DigiKey. One thing to note about this part is only capable of outputting 60 milliamps. So this is something we have to keep in mind. Maybe it's something we should label on the board to say, hey, the output is whatever input current you had, but on the positive rail, but on the negative rail we're limited to 60 milliamps. 60 milliamps should be more than enough for most op-amp applications, but there are certain times where you might be using more current than that on the negative rail, in which case we'd have to use a different design. So let's open the data sheet for this and just take a look at this part. So one thing about the data sheet is it shows us a typical application for this. So this is showing us where different components have to be connected to the component itself. So we have the inverting charge pump regulator here. We have a 1 microfarad, which is the capacitor, which is used to actually charge up and then switch to the negative rail. And then we have an output and an input, which each have a 1 microfarad decoupling capacitor. So we're going to have to use, in addition to this component itself, we're going to have to use 3 1 microfarad capacitors to make this circuit work according to the sort of typical application design. It's always good to read through critical stuff on your data sheet. In this case also, this charge pump switching regulator is probably not going to actually be able to produce if we have an input of 5 volts, it's probably not going to be able to actually produce an output of negative 5 volts. Probably there's going to be a little bit of voltage loss due to losses in those switching FETs. So let's look at how bad it actually is. If we look here, this characteristic curve here, if our input voltage is 5 volts and our output current is 60 milliamps, which we have here, yeah, it looks like in there our maximum output voltage is going to be negative about 4.4 volts. So it's just something to keep in mind that our negative rail is not actually negative 5. At a full 60 milliamps, it's going to be negative 4.4. So whether or not that's suitable for us, we'll have to see. But for the most part, when using an op-amp, the rails are just sort of, they set your limit for your operating range. A lot of times that'll be okay to have, especially if you're using an op-amp that's not a rail-to-rail op-amp. You're going to have a little bit of voltage loss due to as you get close to the rails anyway, so it should be okay. So we have the typical application here. Now, one thing we're going to do is, we talked about finding parts in libraries. You're not likely to find a specific component like this in the library in Altium, but you might be able to find one in the vault. So if we go back to Altium, so this is the TPS 6040, and actually we want to use the TPS 6043, that's the one. If we go back to DigiKey, we have this TPS 6043 DBVR. Let's just copy that for a sec. Let's copy that. If we go into Altium and we go to the vaults, so this is the vault. One thing to note about the vault is here, see how it says Aaron Kramer? He's the lab tech we had several years ago. He was the one who actually configured the preferences files that we loaded. So we're logged in as him to the Altium vault. That's okay. It seems we've been okay having lots of computers logged in as him. But just keep in mind, you see that name there, that's just because our lab tech who set this up years ago logged in with his account. We still have access to the vault just the same. So the vault is searchable and it's pretty good. So let's type in that part number and just see if it shows up. It does show up. So we have this component, it's already here, and it looks like, yeah, we've got it right here. Now, when we're searching for components, when we're looking at components in the vault, I usually like to view them with a preview. The preview is going to show the physical footprint, and it's going to show the so it's going to show both the board part and the schematic part of this component. I really like to use this as a verification. A lot of times a component will be available in lots of different packages. So looking at the actual physical footprint is a good quick way to make sure you have the right package for this part. Also, you'll notice we have, for this one component, we have different footprints. So we have a footprint that says L, M, and N. This usually means they have multiple footprints for different densities of our board design. So when people are doing PCB designs, sometimes they're doing a high density design where they're trying to cram as much stuff in as they can, in which case they're probably going to have smaller pads. But if you've got a little more space to work, it's going to be a little bit easier if you have larger pads that you're using. So we have an option here. I'll show later after we place the part how we choose which one of those we're going to use. But for now, we'll just right click on this part. Oops. And click place. Okay, so we're going to place this guy in right about here, maybe. That's fine. And then hit escape to cancel. Okay, so there's two other things that we need to do this design, or there's one other thing we need. There's three of them. We need capacitors. We can find capacitors by going back to the library, miscellaneous devices. We're going to look for 0603 surface mount capacitors. We can find those in the cap semi here. Cap semi 0603, right click, place cap semi. So we need three of them. So we got to have, again, using the space bar to rotate these, we got to have one for these, one for the actual pump capacitor, one for the input decoupling cap, one for the output cap. Okay. So it's a good idea to space these out so we can see the actual component values here. It's not perfect, but it's probably good enough. So one thing to note, so right now the value for these capacitors is 100 picofarads. You can, if you search the vault, you'll find components that are identical but have a different value listed. A lot of times we don't have to do that. As long as we know we have the right footprint, we can change the value stated for the component. So if I click this guy, I can change this from 100 picofarads to 1 microfarad. It's important to keep in mind, though, that the only thing we've done is change that text. We haven't, by specifying a different capacitance value, we haven't changed anything physically about the system. All we've done is change the text. So, if we typed in 100 microfarads there, it wouldn't give us nearly a big enough footprint for a 100 microfarad capacitor. The only thing is, it's telling us when we do a parts list or a bill of materials that, in fact, that component needs to be a 1 microfarad component. But we'd better make sure that we have that in the footprint that we had for the original part. So I'll do that for all the rest of these too. Oops. Okay. Now, for wiring this together, there's a couple different ways we can do it. We have a lot of what this is a power converter. So we have a lot of power rails here. Usually for power nets, we're going to use these ground and power port symbols here. So for instance, if my input was going to be ground and positive 5 volts, we'll put a ground symbol there, hit escape. Then we'll put a VCC symbol there, but I don't want to use VCC. I want to specify that this signal is 5 volts. So if I click that, I can change this net name to 5V0. Just as a good quick saying, yeah, this is a power rail, but it's a 5 volt power rail. We can do the same thing over here for our output. Our output is going to have a ground, 5 volts, and we're also going to have a negative 5 volt signal here. Let's put another one here. So we'll do negative 5V0. This is actually not ideal. We wouldn't normally want to write a negative 5V0. We'd want to find a better naming convention like neg rail, pause rail, something like that. The negative sign is very easy to miss when you're just sort of quickly scanning this document, so it's not the best idea, but it's good enough for now. Okay, so we have these rails here. How do we actually wire these things up? So one thing is, the way we connect signals electrically in a schematic is either by labeling two things the same thing. So in this case, this pin here and this pin here are identified as being physically connected together because they're given the same label name. The other way we can do it is by drawing a bus. So we can actually, by drawing a wire. So we can actually draw a wire between two things to show an electrical connection, the same way we would in a normal schematic. So to do that, we'll click this place wire, and we will connect this capacitor to the input. We will connect this capacitor to that converter here. We'll connect this capacitor to the output. We'll connect this rail over here. We'll hit escape to exit that wire placement. We've got a couple more ground ports to place, so let's place a ground here. Place a ground here, and now what we have here is we have a circuit that looks a lot like the circuit that we had in our data sheet here. So this circuit in the data sheet has those three capacitors and our component. That's exactly what we have now here. It's just drawn a little bit differently. Mine's a little bit sloppy.
Are you actually talking to somebody on there?
Oh, I'm actually making a video. Yeah.
Oh, sorry.
No, it's fine. It's fine.
Where are the test tubes at?
338.
Oh, okay.
Yeah.
Thanks.
Big bag. Okay, so, one more ground. Okay, so the input though, this input here has got to be 5 volts and this output is -5, so let's do some more rails there. Hit escape. 5V0. Oops. Okay. So now everything is wired up. So we don't show a physical connection here, but it is connected because they're labeled the same thing. Now I want to really quickly talk about moving things in Altium because this is really important. If I click on this header and I move it, look what happens. The header becomes physically disconnected from these signals, which means it's now electrically disconnected. We're identifying to Altium there's no longer an electrical connection here. If we want to move something and maintain those signal connections, what we have to do is click Control and then move it. So if we click Control and then move the part, it will keep those electrical connections while moving it. You got to be careful though, because it can really quickly become ugly. The other thing you can do if you want to move a lot is just select everything and then again just left click to move it around, and that'll work just fine. Now one thing you might notice is these things are each named P question mark, U question mark, C question mark. So right now we've placed these components, but we haven't given them names. Before we actually move this into a board, we need to give unique identifiers to each one of these components. So the process of doing that is called annotation. You can do it manually, but the better thing to do is just have Altium do it for you. If you click Tools, Annotation, Annotate Schematics, it'll open up this automatic annotation tool, which will sort of scan through your design left to right, top to bottom, and it'll sort of incrementally give names to each of your components. We're going to click Update Changes, OK, Accept Changes, Execute Changes, Close, Close. And what that did is now you see we have U1, P1, P2, etc. So we named all these components. So if we're happy with our design and we think we have everything we need for our circuit, and it looks like we pretty much have everything we need, the next step is to export this to a board. So we will, right now, we're going to leave it at here for this video. So we'll go File, Save All, and then we'll come back to it and do the board design later. Okay, thanks for watching.